I'm super happy to be introducing Monika Aidelsburger today. So I personally became aware of your work, Monika, when you were still a PhD student doing the artificial gauge field initial type of work in optical lattices. That was for the students, that was originally plaquettes before merging the plaquettes into full system gauge fields. After that and the related family of work, Monika went off to do a postdoc in Paris and switched to systems that are a lot more like continuum systems before being lured back to the appeal of lattices, where she's continued to do wonderful work thinking about gauge fields of a more dynamical variety. Just in addition to other things, I'm going with the gauge field theme here because it's particularly awesome. And at this point, looking at the CV, I see that you've become a proper professor for a couple of years. So I think Monika is one of the youngest speakers here, yet if you look at her CV and blocked out the age part, you would have no idea. So welcome, Monika, and let's see, so we're live on YouTube, so we're good to go.
Yeah, thanks a lot, Ian, for this very nice introduction. I'm very happy to be here. Actually, I seem to be trying to get to the Boulder Summer School in person. I think I was trying last year, this year again, and I will try again next year. So let's see, maybe at some point it will actually work out. So I will talk about engineering gauge fields. Let's see towards the end of the lecture if I will say a bit more about spin orbit coupling as well, but I will mainly focus on gauge fields and maybe tell you a little bit of our work, also what we have done in order to make these gauge fields dynamical. Now, I will actually start with a bit of a repetition also about Floquet, something that Tillman already discussed in one of the lectures before, or some of the lectures before, because the laser-assisted tunneling that we are using is very much related to that technique. So in case I'm going too fast or too slow, I really need your help here because I don't know all the details that Tillman already mentioned. So please feel free to give me some feedback here. Okay, so actually also just to start, I also wanted to show you a picture of our lab here in Munich. You've already seen that, I think, also in Ian's talk and probably also some of the other talks. So this is an example from our cesium lab, which we are just setting up. So here you see Till, one of our PhD students, working on the setup. So on the right here, we have our cesium oven covered in aluminum foil. And then in our cold atom experiments, we have this regular cycle where we cool our atoms to low temperatures and then perform some measurements on them. So what you see here in the middle is this long section, the Siemens lower, where we have this magnetic field gradient where we send in a laser beam from the other side in order to slow down our atoms. And then in the back, you don't really see it behind all of these optics, but there's another vacuum chamber where we have a magneto-optical trap set up and Raman sideband cooling to get to temperatures on the order of a few microkelvin. And then our chamber has actually this L-shaped configuration. So in between these two preliminary coils, so now they have been actually replaced, you see a tiny glass cell where we perform all the science experiments. Here we have a very good vacuum of around 10 to the minus 11 millibar. And there we generate a Bose-Einstein condensate of cesium atoms. And if you were to zoom in on this tiny section of the vacuum system, then you see this nice glass cell that we have with different viewports to send in the different lattice laser beams, and where we have our high resolution objectives to image the atoms from the top and the bottom. So the starting point of our experiments, I guess I don't need to tell you, but is either Bose-Einstein condensate or degenerate Fermi gas. I will almost exclusively talk about non-interacting physics for this engineering of gauge fields. So it actually doesn't matter all that much if you work with bosonic atoms or fermionic atoms. But to keep in mind, I will mention that for the initial state preparation, when we work with Bose-Einstein condensates, you can think about them as being all prepared in the lowest energy eigenstate of the system. And then in many cases, we can use semi-classical descriptions of wave packet dynamics in order to extract the geometric properties of the energy bands, something that I think Nigel also talked in his lecture about. And then from there, we adiabatically prepare our atoms in optical lattices that we generate by interfering laser beams using the AC stack effect. So they are very far detuned from any internal transition. So typically, if we interfere just to counter-propagating laser beams that have the same frequency and same polarization, they create a standing wave, and then the atoms will see this periodic landscape where the minima between two sides, the distance between two sides is on the order of the wavelength of the lattice. So that's the starting point for us to think about how to engineer something more complicated. So the atoms, the dynamics of the atoms can be described by Hubbard models, either Bose or Fermi Hubbard systems. So we have this kinetic energy term that is proportional to J, the tunnel coupling between neighboring sites, and an interaction energy scale U for the atoms when they are on the same site. And we can actually control these microscopic parameters with different techniques. So changing the tunnel coupling means changing the intensity of the laser beams, and changing U can be done, for instance, by using Feshbach resonances. So the system is very nicely isolated from the environment, and we have a very good control. Okay, so but here we are interested in engineering gauge fields. And our technique is actually very closely related to what Tillmann has been reporting. So I will actually pick off the discussion from there. So this is the last slide I'm going to show, and then I actually wanted to walk you through the calculation in a little bit more detail by taking notes on my iPad. So just to remind you about what we want to do. So we want to make our system more interesting, adding gauge fields. So we want to make it topological. And the way we do it is using the technique of periodic driving or Floquet engineering. So we have this time-dependent Hamiltonian, h of t, where capital T is the period of the drive. And then, as was nicely explained by Tillmann, we can describe the stroboscopic time evolution using this effective time-independent Floquet Hamiltonian HF. And then we want to engineer or use a periodic modulation technique such that this Hamiltonian HF shows some interesting properties, which in our case means we would like to engineer gauge fields or make the bands topological. And something that maybe I will mention in the third lecture or maybe at the end of the talk as an outlook. Now we have this quasi-energy spectrum because the quasi-energy is only defined up to integer multiples of the driving energy quantum h bar omega. And this can actually be used in order to engineer more interesting phases that actually do not exist in static realization. So we can actually even use this technique and go beyond just simply emulating the physics of static systems and engineer something new, which is called anomalous Floquet systems. Okay, so but let me now change to my iPad and write some notes on the technique that we have been implementing. Is that okay? Does that look good? Yeah.
Yeah, looks good.
Okay, thanks. Okay, so just as a recap, what we are interested in doing is engineering an artificial magnetic field. And we use laser-assisted tunneling in order to do that. So in the end, the goal is to have, in our case, a square lattice with artificial magnetic field. So we have a flux piercing the unit cell of the lattice. And this is done by engineering complex hopping matrix elements. And as a recap, for these time periodic systems, we can use Floquet theorem in order to write down the time evolution. And what you have seen on the previous slide is basically the formula that we can use in order to describe the stroboscopic evolution of the system. But the general form of Floquet's theorem also includes the micromotion, so what happens within one driving period. So we can write down our time evolution operator between 2 times t initial and t final, according to some kick operator, which is here incorporated in the operator P, and time evolution according to our Floquet Hamiltonian. So this P is defined as e to the minus I k tf, where k is the kick operator, which is also periodic in time. Okay, so T initial is called Ti, and Tf is the final time. So we can think about this general form of the Floquet or time evolution operator of Floquet's theorem as follows. We have some initial state psi 0 that we prepare. And then there are 2 contributions. So there's first this unitary operator P, which somehow rotates our system into a time-dependent frame. So this is also what describes the evolution during one period of the drive. So I think you have seen that we can think about this time periodic system as some stroboscopic evolution, which is governed by HF. So this is the slow evolution of the system. And then on top of that, we can have fast oscillations, and those are described by this operator P or the kick operator K. So we can think about this time evolution really as applying some initial rotation. Then there's a time evolution between the initial and the final time that only depends on this Floquet Hamiltonian HF, which is time independent. And then we rotate back into our lab frame. And there's this whole family of Floquet Hamiltonians, which describe this long time dynamics of the system. And they are all related by gauge transformations. So the simple form of Floquet's theorem that I've shown on the slide is actually by taking T final minus T initial to be equal to N times T. So that would be the stroboscopic evolution. And then we forget about these kick operators. But now the computation of the actual form of HF would depend on the initial time that I choose. And this initial time dependence can be described as a gauge transformation. So there are these families of Floquet Hamiltonians which share the same spectral properties and also the same topological properties for the energy bands. But then depending on the observable that you measure in the experiment, as you see, according to these fast oscillations, you may get a slightly different result. So if you want to actually describe what happens in the experiment, you have to take that into account as well. And okay, so we can actually always write down this form of Floquet's theorem. And now in particular, if we choose this modulation frequency to be very large, we can compute an analytic form of HF by making a series expansion in powers of 1 over omega. And here I want to recap something that Tilman already mentioned in his lecture, 2 methods on how this can be done. And then I will actually use the second one in order to compute the effective Hamiltonian for the laser-assisted tunneling technique. So the first one, which is actually very convenient in order to calculate both the effective Floquet Hamiltonian HF and the kick operator K, is based on commutation relations. So by imposing the condition that you want to find HF being time independent, you can find a series of recursion relations which allows you to compute HF and K. So we assume that we have some Hamiltonian H of t, which consists of a time-independent one, h0, plus some perturbation, v, which is time periodic. So we can make a Fourier expansion of v of t. So it would be the sum over different terms where we denote the different Fourier components as v to the power of n. So we have e to the I n omega t plus counter rotating terms, e to the minus I n omega t. And so in the high frequency limit, hf is given by h0 plus 1 over h bar omega. That would be the first order contribution to the Floquet Hamiltonian, which is the commutator between Vn and the counter rotating term, plus higher order corrections. So of course, if omega is very large, then this lowest order contribution will already be very good in order to approximate the Floquet Hamiltonian HF. And then the higher order terms are actually commutators between the Hamiltonian H0 and the perturbation V. Plus higher order terms, which go as 1 over omega to the power of 3. And similarly, we can compute the kick operator, which to lowest order basically only is determined by V, the perturbation that we apply. But there's a second technique which allows you to compute the Floquet Hamiltonian, which in some sense, I think is very intuitive. But in order to do it consistently, including also the micromotion, would be a little bit more complicated. But if we forget about the micromotion for now, it's very useful because using the Magnus expansion, you can think about this periodic driving technique as simply some very fast perturbation, which you can average over. So the lowest order contribution in the Magnus expansion is basically the time average over h of t over one driving period. But of course, you can also do that consistently if you want to also study the micromotion. So again, we have this series expansion of HF of different orders in powers of 1 over omega. So it's HF n, so to speak, to count 1 over omega to the power of n, where the lowest order HF0 is now given by 1 over t, where t is the modulation period, and then the time average over h of t. And then again, there are higher order terms, which actually involve commutators. Okay, so now I think many of the examples can actually be understood in the regime of off-resonant driving. So there, what we assume is that this additional perturbation V of t does not have any frequencies that are resonant with any of the energy gaps of our Hamiltonian H0. However, in this laser-assisted tunneling technique, we use precisely one of these resonances. So actually the perturbation V of t, this periodic drive, happens at a frequency that is resonant with a gap of H0. So if we impose this resonance condition, then you can actually not easily take the high frequency limit, because the high frequency limit, what does it mean? It means that you send this modulation frequency to infinity. However, if you now impose this additional condition that there's a resonance between this driving frequency and an energy spacing in your spectrum, then you have a term appearing in your Hamiltonian, which diverges when you take the limit omega to infinity. So in order to describe that system, we have to get rid of these diverging terms. And it is usually very convenient to do that by transforming into the rotating frame. And I give you an example in a second. And we denote this term as H omega. Okay, so now in order to get rid of this term, we apply a unitary transformation. Where we define the unitary operator as R of t being e to the I H omega, this diverging term, divided by H bar. So if we apply this transformation, we obtain a new Hamiltonian in the rotating frame, which is now this curly H, which we can compute as follows. So we have R of t applied to H of t, R dagger, minus IH bar R dt R. Okay, so essentially this term is what removes the diverging term in our Hamiltonian H of t. And then we can analyze the properties of this Hamiltonian instead of treating the original one in the lab frame. And now there's a simple example to understand in principle the whole scheme that we use in order to engineer gauge fields. So it's enough to actually consider a two-level system in the presence of a resonant periodic drive. And because we have studied that also in the lab, I will just take a double well instead, but you can think of any two-level system that you like. So we have two levels, 0 and 1. And there's a large energy offset between the two, and there's a small coupling between the two, such that in the case where this energy scale delta is very large, the eigenstates of the system are essentially given by the uncoupled ones, which are denoted as 0 and 1. So the energy difference or the energy gap in this system between the two states is given by delta squared plus 4j squared. And if I take delta over j to infinity, it's essentially given by the two bare states which have an energy gap delta. Okay, so now we add a resonant modulation at a frequency that matches this energy offset delta. And just to simplify the calculations, I will choose to add it to one level only. So in this case, it would be to the A side in this double wave potential. So our Hamiltonian is actually very simple. So we have h of t. We have some coupling term proportional to the coupling J that mixes the levels 0 and 1. We have h bar omega times the excited state. So here I already impose the resonance condition, right? So I've told you that I want to add a driving that is resonant with this energy difference delta. So if I plug that in, this term actually diverges if I send omega to infinity, which I would do if I want to take the high frequency limit. And then I add an additional periodic modulation, V times cosine omega t, which has some phase phi. And as I mentioned here, I added to the A side of the double wave potential. Okay, so now this system can be conveniently treated if we apply this transformation into the rotating frame. I just see that there was a question. Yeah, sorry, let me come back to this
okay.
energy gap. So basically what I did here is, this two-level system we can describe by a 2x2 matrix in the spaces of the levels 0 and 1. So essentially what we have are some off-diagonal elements according to the coupling J, and there's an energy gap between the two expressed by delta. So now if you diagonalize this matrix and compute the new eigenstates of the system, they will have a small admixture. So the level 0 will have a small admixture of the level 1. And the eigenenergies, the difference between the two eigenenergies is given by this expression. Okay, so now we apply this transformation. Into the rotating frame that I mentioned. And we will actually add an additional term because it makes the computation even more simple. So we will define an R of t as e to the I omega 1, which is basically the term that I mentioned up here to get rid of the divergence. But then we will add an additional term plus I over h bar. And then we integrate over this perturbation V of t, which is our periodic drive. So V of t is this V0 cosine omega t plus phi. So in the end, our unitary transformation will be according to R of t, which is e to the I omega 1 plus I V0 over h bar omega sine omega t plus phi. Now, after applying this transformation to the rotating frame, we actually find a new Hamiltonian, which simply consists of coupling terms, which, however, are now time dependent. So what we actually do with this transformation is to move the time dependence that we had in the Hamiltonian, that was proportional to diagonal terms. So we move this time dependence to the off-diagonal elements. So we find an h of t, which is j 0, 1, e to the I, and now I introduce this little eta plus the Hermitian conjugate. Where now eta of t is defined as minus omega t minus v0 divided by h bar omega sine omega t plus phi. Okay, so far I haven't done anything. I just applied a transformation into the rotating frame. And the reason for that is that the calculation becomes much more simple in this rotating frame. Now, this Hamiltonian is still time periodic. So this Hamiltonian has the same periodicity as the original one in my lab frame. So I can apply Magnus expansion in order to compute the Floquet Hamiltonian. Okay, so now I go back to the formula that we had above. The lowest order will be simply given by the average over one driving period of my Hamiltonian h of t. Okay, so now HF is approximately given by 1 over t and the integral over h of t dt. So now I can introduce this new variable tau, which is defined as omega times t. So I will find an integral now renormalized by 1 over 2 pi, integral from 0 to 2 pi over my Hamiltonian h of t. So just to be very clear again, t is equal to 2 pi over omega, where omega is the modulation frequency. Okay, so now I'm running out of space. Okay, so now I have this integral. And actually now you can recognize that this integral is the integral form or representation of a Bessel function. So what we will find is that now this lowest order of the Floquet Hamiltonian is given by an effective coupling matrix element, which is proportional to the original one, J, and then scales proportional to the first order Bessel function, J1. And this phase factor here, we can simply move in front of the integral. So what we will find is this effective hopping matrix element, where now we have an additional phase factor. Okay, so in the presence of a resonant drive, we actually now have restored coupling between the two levels. And the effective coupling matrix element is renormalized according to the first order Bessel function of the first kind. The argument that defines the strength of the induced tunnel coupling is defined by the modulation amplitude renormalized according to the modulation frequency. And depending on the phase of the modulation that we apply, we can engineer different complex hopping matrix element if we use this first order photon process. And this whole calculation can be generalized relatively easily to include higher order photon processes. So if we relax this resonance condition where we have chosen h bar omega equal to delta and allow for an integer number of multiples of h bar omega to bridge this energy gap, then different restored hopping matrix elements can be engineered. So I've introduced this integer nu just to generalize this resonance condition. Let me write that in a more nicer form, which following the same derivation will result in a Floquet Hamiltonian, which has an effective coupling matrix element, again proportional to J, but now the first order Bessel function of the nth kind. Nth order Bessel function of the first kind, sorry. And this additional integer nu also shows up in the phases of the complex hopping. Just a second. So there was a question if we actually need the amplitude of the modulation to be small in this case. No, actually not necessarily. Typically, we work in the regime where indeed the modulation amplitude is small compared to the driving frequency. And this is the regime, which I will show in a second, where we have actually a linear scaling between the modulation amplitude and the induced tunnel coupling. But you can actually, even in the strong modulation regime where V0 is relatively large, you can still derive this effective Floquet Hamiltonian. So it's incorporated in this Bessel function, which we will see in a second. So I will show you a plot where we scan the effective tunnel coupling as a function of V0 divided by h bar omega. And just for completeness, I also give you the definition of J nu of x, which is 1 over 2 pi integral from 0 to 2 pi e to the I nu times tau minus x sine tau. So in this high frequency expansion, omega is large compared to J. Okay, so that's also a very good question. So the question is what happens if omega is slightly detuned from delta? If you go through the derivation, you will actually see that in this unitary transformation, we get rid of the diverging terms. So we actually have this term e to the I omega applied to level 1. And if you compute the Hamiltonian in the rotating frame, you get, so let me go back to the, so you have this term, which actually gives you an h bar omega, which cancels the h bar omega term here. Now, if you detune it a little bit, you will be left with a small energy offset here. So you will have a small additional term, delta omega, between the two energy levels 0 and 1. Does that answer the question? Okay. So maybe something to realize if you go through this derivation is actually that you also get this renormalization of the hopping, even if there was no energy difference to begin with. Okay, so we could consider actually the case nu equal to 0. So in this case, you would have a renormalization of the hopping matrix element according to the 0 Bessel function. So in our double well picture, this would be a symmetric double well, no energy difference between neighboring sites, but nonetheless, you apply a periodic drive. Where we shake this well up and down as a function of time. And in this case, there's a renormalized hopping matrix element, which goes down as a function of the modulation amplitude. Okay, so let's have a look at how that looks, and I will get back to the question of small modulation amplitude V0. So we can actually measure this renormalized hopping J effective in experiments by recreating exactly what I've just mentioned, that we take a double well system or a two-level system that is weakly coupled, and we apply resonant periodic modulation. So this we can do by using superlattice potentials, where essentially we chop our lattice into small pieces, disconnected double wells, where all the dynamics is restricted only to two sides. So in the experiment, we can overlap two lattices, here shown as blue and red, where the lattice constants between the two have a ratio of exactly 2. And this creates such a double well potential where if we take this barrier to be very large, there's essentially no coupling between these two sides, and all the dynamics is restricted to any individual double well. And then moreover, we can prepare a single atom within one of these double wells in order to measure the tunnel coupling between neighboring sites. So the idea is that initially we prepare a single atom in the double well. So let's say we put it on the low energy side. Here we have this energy difference data. And then we suddenly turn on the modulation. So in our effective Floquet Hamiltonian, we now have a symmetric double well. We resonantly couple the two states, but now they are coupled with J effective. So if we measure the oscillation of this particle between the left and the right side as a function of time, so we get Rabi oscillations between these two sides, then we will be able to extract from the modulation frequency the tunnel coupling J effective. And this we can do for various different resonance conditions. So we can do this experiment by removing delta completely, or we can choose the condition h bar omega equal to delta, 2h bar omega equal to delta, and so on. So what we will see in the experiment is time traces of the following form. So that's a bit too big. Well, I put it on the next slide. Where you see these oscillations So -1 means the atom is prepared on the left side. It starts to oscillate between the two sides. So this value of 1 means it's on the right side of the double well. And then by fitting this oscillation frequency, we get a value for J effective. And here you see 3 different examples. One for the symmetric case, the first order resonance and the second order resonance. And if we plot this as a function of the driving strength and perform this measurement for various different values, then we get a calibration of the renormalized tunnel coupling J effective. And this is what you see here. So this is a measurement that we took in the lab, where the solid lines are really just theory prediction. So there's no free fit parameter. There's no, if all the parameters are calibrated independently, this really works perfectly. And here you see what happens in the symmetric case. So here you have the renormalization for the symmetric double well, where as a function of the modulation amplitude, the effective hopping goes down. And there's even a point where it reaches 0, where tunneling is suppressed completely. And here you also see the driving strength. So this is not necessarily a small parameter. It actually goes here up to a value of 2. And for the first order resonance, it's similar, up to a value of 2 shown here. But for low modulation amplitude, it starts at 0, and then it increases linearly with the modulation amplitude. And then there will be the shape of the first order Bessel function, and the same for the second order process. So this calculation for the effective Floquet Hamiltonian works even if this parameter psi, which is the renormalized modulation amplitude, is not very small. But what one has to keep in mind is actually also the transformation back into the lab frame. Okay, so this modulation that happens within one driving period is neglected in this description that I've shown you. I just showed you how the Floquet Hamiltonian looks like for the stroboscopic evolution of the system. But as we said, there are fast oscillations on top. And the amplitude of these fast oscillations depend also on this ratio V0 divided by h bar omega. And actually, if we stay in this low driving regime, somewhere here, you can approximate the Bessel function for small arguments psi. And what you will find is that here, it scales linear with psi, the effective hopping matrix element. And here to first to lowest order, actually nothing happens. And then it decreases quadratically with psi. So this regime is in a sense equivalent to what we know from the rotating wave approximation. But then if you make the modulation amplitude larger and larger, we will leave that regime, because at some point V0 is on the order of the modulation frequency omega. Now, there has been also a question about the damping of the oscillations that I show here. So here you see the nice Rabi oscillations between the left and right side in the double well. And the damping that you see here is actually due to an averaging that we do in the experiment. So the way we realize these isolated double wells is by generating such a superlattice, which chops a 1D chain into these isolated two sides. But then in addition, we have a 3D system. So we actually average over many of these double wells. So there are a few hundreds of these double wells. And because initially our atoms are confined in a harmonic trap, not all of these double wells are equivalent. And maybe the easiest way to think about it is just plotting the double well in the presence of the harmonic confinement for a 1D chain, which would look more or less something like this. So you have a symmetric double well in the center. And then towards the edges of your system, because you have a harmonic trap, there's a small additional energy difference, which is in a sense leads to detuned Rabi oscillations. That goes back to the question that we had before. If now we introduce a small detuning, so omega is not precisely equal to the energy difference delta, then we have an additional detuning term here appearing in our Floquet Hamiltonian. So we have a coupling between the two states and a small detuning delta omega, which leads to detuned Rabi oscillations, which have a different frequency as compared to the resonant Rabi oscillations. And in the end, the observable that is plotted here is averaged over all double well realizations, which leads to this dephasing that shows up as a damping of the Rabi oscillations. Okay, so I actually have additional references in my notes. I will not write them all down here, but the ones that I upload, they will contain additional references for you to check if you want to read more. Okay, so now actually doing this in 1D works very similar. The only thing that one has to be careful about is this modulation phase phi, so the phase that we apply in this periodic modulation, and how it shows up in the effective tunneling amplitude, so the amplitude of the effective tunneling and the phase. Okay, so now we consider a situation which is very similar to the double well, but we just add more sites. Okay, so we have this bare tunnel coupling J between neighboring sites and some energy offset data, which now increases linearly as a function of X. And now we introduce this site index M and M+1. And we add a periodic modulation. V0 sine omega t phi, which now has this index M. So generally this phase of the periodic modulation is different between neighboring sites. And now we can use the same machinery that we have seen before in order to derive the effective Floquet Hamiltonian in the rotating frame. So if we choose the first order resonance, h bar omega equal to delta, then there's a Floquet Hamiltonian with an effective tunnel coupling J effective, which is proportional to the bare one and the Bessel function. And now maybe as a side remark, the argument that appears in the Bessel function now does not only depend on this renormalized modulation amplitude V0 divided by h bar omega, but also on the relative phase between neighboring sites. So this eta 0 is defined as 2 V0 divided by h bar omega, similar to what we had before. But now there's an additional term, sine of the phase difference, phi M+1 minus phi M. So let's think a little bit about what that means and why it makes sense. So actually what it says is that if phi M+1 and phi M are equal, then the argument of the Bessel function is 0 and we don't restore tunneling. And now, okay, what does it mean that phi M+1 and phi M are equal? It just means that this periodic modulation that we apply is exactly the same on each one of these sites. So the only thing that we are doing is shifting the global energy up and down periodically in time, and this will not do anything to our system. So in order to be able to restore hopping between neighboring sites, what matters is the relative modulation amplitude. So you will actually get to the maximum amplitude of the periodic modulation if this shaking is out of phase by pi between neighboring wells. Okay, so this relative phase difference between neighboring sites is actually not showing up in the phase of the complex hopping, but it shows up in the amplitude of the restored hopping. And then this phase that appears here, phi M, is defined as the average between phases on neighboring sites. Okay, so let me just show you a plot for this renormalized modulation amplitude for different modulation parameters. So here what you see is actually a 2D plot of the Bessel function, the restored hopping as a function of this phase difference delta phi, which is, delta phi x is phi m plus 1 minus phi m, and eta 0. So if we take a vertical cut here along this line, you see the Bessel function behavior that I've shown you before. So this is actually an example for phase difference that is equal to pi. But now you can also take a cut along this horizontal line where we scan this phase difference delta phi. And you see that if this phase difference is 0 or if this phase difference is equal to 2 pi, nothing happens. And you get the largest response for the value where the phase difference is equal to pi. Okay, so now we have found a way that allows us to generate complex hopping matrix element. Okay, so we know how the hopping is restored, and we also know how the phase appears in this matrix element. So we can extend it to 2D. And since we already have what we want along this 1D axis, so we have this complex hopping matrix element e to the I phi, we can simply extend this 1D lattice by adding a second one perpendicular to it, which has just a bare hopping according to some tunnel matrix element JY. Okay, so now we consider this 2D lattice, where along X, we apply this energy offset delta. So there's no hopping if this condition is fulfilled. And perpendicular, we have this bare simple lattice where we have hopping between neighboring sites according to JY. And now in order to have laser-assisted tunneling along X, we add a periodic modulation. And now the question is, how can we conveniently realize this periodic modulation in the lab where we actually want to have something like that? So we want to have a potential that periodically oscillates with the frequency omega, but has this spatially dependent phase, phi m. And so what one can do is to add 2 additional beams that realize the periodic modulation. So in our example, we use 2 beams here with wave vector k1 and k2, frequency omega 1 and omega 2, which are far off resonant. And due to the small frequency difference, omega 2 minus omega 1, they will generate a time-dependent potential. So these 2 beams actually interfere, and up to constant terms, we can write down the potential as a function of position and time. So there will be some modulation V0 times cosine omega t plus some phase phi of r. So you can just try to do that yourself. You have 1 beam coming from X and 1 beam coming from Y, and then you calculate the time-dependent potential induced by the AC-Stark effect that the atoms see. So if you look locally on one specific site in the lattice, there's a potential that periodically oscillates as a function of time. And if you look at the neighboring site, you see exactly the same thing. There's the same potential that oscillates as a function of time with this amplitude V0. But in addition, it has a different phase. Okay, so there's a relative modulation amplitude between neighboring sites, which is non-zero and which can restore hopping along that specific direction, where we have initially had this energy offset data. And this phase phi is determined as delta k times r, where delta k is the wave vector difference between the two beams that we shine onto the atoms. And then we again choose the resonance condition omega 2 minus omega 1 equal to delta. Okay, and now you actually don't have to do any calculation anymore because I already told you everything and how it works in the effective Floquet Hamiltonian. So again, you can apply the rotating wave approximation, calculate the lowest order of the Magnus expansion. And then what we will find is that there's a lasers is the tunneling direction. So restored hopping occur according to the first order Bessel function of the first kind. And then here, actually nothing happens, but there will be some renormalization due to the periodic modulation. So in this specific example that I've shown here, where we have two beams, one coming from this direction and one coming from this axis, there will be an interfering wave or running wave diagonal across this lattice. So there's both, there's periodic modulation between neighboring sites along this bond, but also there's a periodic modulation between two neighboring sites along the perpendicular bond.
Sorry, I have a quick question.
Yeah.
How homogeneous is V naught across the full lattice?
So that depends on your laser beam parameters, but it can be very good. So essentially what you have to compare is the Gaussian profile of your laser beam. So you send one from X, so this laser beam will have a certain waist. And if this waist is large compared to the size of your atomic cloud, which is just a few micrometer, a few tens of micrometer, then you can make it very homogeneous. Also because the amplitude that you need is not very large. It's a resonant process, so you don't need a lot of laser power in order to generate this potential. So you also don't run into power limitations typically. So you can really make it very nice and homogeneous.
Thanks.
This is kind of a related question. So here you've assumed you have this nice linear tilt and the delta, the deltas are constant. Right. Are you thinking about really having that, or are you in a harmonic trap and only some part of the cloud is resonant?
Yeah, good question. So in this particular example that I had in mind, but it doesn't actually matter. So you can either generate this potential optically, or you could use a magnetic field gradient if you work with a Zeeman level that has a non-zero magnetic moment. Using a magnetic field gradient will generate very nice linear potential. So there you don't have to worry about any additional nonlinearity. For optical beams, that may be the case, but also actually on top of that, there's typically a harmonic confinement, right? Because the cloud is actually confined in a harmonic trap in the first place. But if you go through the derivation of this unitary transformation, which basically consists only of local density terms, they commute. So this will always show up as some additional detuning. So if you have some inhomogeneity in the system, you will be left with a residual confinement. And now you may ask, okay, what does it do? Does it mean that maybe you don't engineer resonant hopping in the center? Well, as long as this detuning is small compared to your effective coupling, it doesn't really matter. It's like detuned Rabi oscillations, like how you think about coupling two levels just by a resonant drive. Only if this detuning becomes large, then at some point you will be off resonant and not coupling the sides anymore. But in this effective frame, it's really like a harmonically trapped cloud in a usual lattice where you have actually the same problem, right? You also have the tunnel coupling, resonant tunnel coupling between neighboring sites, but then there may be some small potential energy difference due to the harmonic confinement. So it's exactly the same thing.
Great, thanks.
But yeah, to keep in mind, these if you go and have a look at this restored hopping matrix element, you see that it always decreases your energy scales, right? So this is actually the first order Bessel function of the first kind. And 1 would mean that you restore the same bare hopping J, which if you have this driving to restore tunnel coupling, you will never reach. So you will actually always end up with tunnel couplings that are smaller than the one that you had originally. So you may have to worry more about the effective energy scales in your lattice. Very good. Other questions? Okay, so now we have 2 different axes with restored hopping matrix elements. So along X, we have effective hopping, which is proportional to Jx and the first order Bessel function. And those effective hoppings are complex. And now I added this additional index n, which is the lattice index in the perpendicular direction. And then along y, there's also a renormalization, which is, however, negligible for small modulation amplitudes. And it is not complex. Okay, so along this direction, we still have a bare hopping. And now you see that actually the complex hopping is induced by the modulation along the laser-assisted tunneling direction. But then if you compute the effective magnetic field for one plaquette, it's related to the difference between the phases along these 2 bonds. So what actually matters in order to define the artificial flux is how this phase depends on lattice index n, which is the one perpendicular to the laser-assisted tunneling direction. Okay, so this is really essential. If you were to choose a configuration where these 2 beams would be aligned, let's say along the laser-assisted tunneling direction, there's no flux. You can engineer a non-zero gauge potential, but you can gauge it away. It doesn't give rise to any non-trivial physics in that case. Okay, so let's take a specific example just to have an intuitive picture in mind. Where now the wave vector is chosen at a very specific ratio with respect to the lattice constant A. Okay, so this gray profile shows the interference pattern between the 2 red beams for one point in time. And so essentially you see the phase fronts of this interfering potential. And between these 2 gray lines, the phase advances by 2 pi. So if you discretize it with the underlying lattice, you see that between neighboring sides, the phase advances by pi over 2. So for this specific choice of the wave vector and the lattice constant, the ratio of the 2, the phase increases linearly by pi over 2 along x and along y. So in this case, phi, you can simply read it off. The effective flux per unit cell is given by pi over 2. But in general, it is given by the projection of the wave vector difference of the 2 beams times A, the lattice constant. So you see that this is actually purely geometric calculation. You can change the angle of these 2 beams or the ratio of wave vector over lattice constant in order to engineer different types of fluxes if you want. So this has really a large tunability and doesn't really depend on the atom. It doesn't depend if you want to implement that with bosonic atoms or fermionic atoms. You could even like implement it with something more complex like molecules, but it works in the same way. And then the phases that appear are really just geometric values. Okay, so now in order to implement this experimentally, what one can do is very easily measure resonances. So similar to what I've shown you before in the double well, where we compute or where we calibrate the effective tunnel coupling between neighboring sites. Similarly, you can also take a spectroscopy, measure where's the frequency of the modulation resonant with the energy difference between neighboring sites. But then what is a little bit more interesting is to get a handle on this effective flux that pierces one unit cell, because that's actually the one that you would want to calibrate in the experiment. And now you can say, well, I just apply this effective magnetic field to my whole 2D lattice and measure something more complex. So we will discuss that actually tomorrow, looking at how we can measure the topological properties or the geometric properties of the bands. But there's another small toy experiment that one can do. And now you can imagine that instead of just having a double well where we want to measure the effective renormalized tunnel coupling, we can extend it to the smallest 2D lattice that you can think of. So we can generate a plaquette and try to see the dynamics in the presence of the effective magnetic field. Okay, so now we chop our lattice into small plaquettes. And we use the same technique as I've shown you before. So we have a superlattice along X and a superlattice along Y, such that if this barrier is large enough, the dynamics is restricted to only 4 sites. So now if I prepare a single atom in this plaquette, it can only explore this area. It cannot tunnel between neighboring plaquettes. And in this specific configuration, we can make a small toy experiment in order to extract the value of the flux directly from the experiment. So the initial state, sorry, that's not the initial state. The initial state is an atom, a single atom, prepared in this tiny lattice of 4 sites, which is delocalized on the left bond between the site A and D. And now you can do a quench experiment and turn on the tunnel coupling in this little plaquette. And then if you track the mean atom position in this little plaquette, you will find that it oscillates between the left and the right bond. So it will just undergo Rabi oscillations between the left and the right bond. But now in the presence of a flux, so if we just turn on the tunnel coupling and quench to phi non-zero, the dynamics should be more complex. And we expect something to happen perpendicular to this initial direction of tunneling, which resembles a bit what we know from continuum, which resembles the Lorentz force. So we expect that the mean atom position gets deflected perpendicular to this initial tunneling direction. Okay, so what we track is now the mean atom position in one of these plaquettes. And again, we actually average over a whole array of plaquettes, so there will be some dephasing and damping of the dynamics. But the result that you get looks something like this. So you see that initially, so this is the mean position along Y, this is the mean position along X, and this point over here at minus 0.5 actually means this is a perfect initial state where the atom is delocalized on the left bond. So this corresponds to minus 0.5, and being delocalized corresponds to 0 along Y. So that's somewhere over here. Initial state preparation is not perfect. That's why you see that it's reduced compared to 0.5. And without phi being present, so sending the artificial field to 0, would mean that we observe Rabi oscillations along this horizontal line. It would just tunnel back and forth as a function of time. Now, instead, what we see is there's actually this chiral motion that shows up. So there's some deflection perpendicular to the initial tunneling direction. And we can, of course, also just compute the time evolution. It's only 4 sites. It's a 4x4 matrix. And this is what you see here in the inset. So this actually matches quite well what we would expect in experiments. And you can also fit this evolution in the plaquette in order to directly extract the value of the artificial field that has been generated. So in this case, we actually extracted from fitting the dynamics that we measure a value that is equal to 0.73 times pi over 2. So ideally, choosing this configuration that I depicted above, we would have expected a value of pi over 2. So it's exactly this configuration that I've shown you. But now we measure something that is a little bit smaller than that. And the reason is that the distance between 2 sites in the double well is a little bit smaller than the lattice constant that you would get in a homogeneous lattice. So the 2 sides, of the double well are a little bit squeezed together. And since the phase occurs just purely due to geometric reasons, it's also a little bit reduced. So calculating the difference between A, the lattice constant in the homogeneous lattice, and the actual distance in the double well agrees very well with this reduced value of the flux that we can calibrate in the experiment. And maybe here I want to mention again, I think you already heard it in some of the other talks, also by Ian, that this technique, how we engineer this flux, is very similar to how the complex hopping appears using the concept of synthetic dimensions. And I also want to show you some recent measurements that have been obtained with dysprosium atoms, where this nice lattice cyclotron orbits also have been resolved in synthetic dimensions. So Monika, just as a quick, yeah.
Sorry, before going on, I was just wondering, so all of this simulated dynamics and what you're observing here is non-interacting, basically?
Yeah, so it's actually really very simple in a sense. I mean, I think it's cool that one can do that in experiments, but really what you do is you put a single atom into this tiny plaquette.
Mm-hmm. So I mean, do you really have control over that, or are you just working at a very low density so that it's rare that you have 2 per plaquette? Sorry, I missed how you were actually loading the initial state here.
No, that's a good question because I haven't really said anything about that.
Okay.
So, yeah, so the way we do it is usually to create a mod insulating state, n equal 1 filling in the long lattice. So we remove these barriers here. So we merge them into like long lattice vials, and we create a mod insulating phase in this lattice. So we have 1 atom per side. And then we can tilt them diagonally so that actually this side and in each one of these plaquette realizations is actually the side with the lowest potential energy, so that the single atom goes there if you turn on the superlattice potential by turning on this barrier. So then you have an initial state where actually here on each one of these plaquettes, there's an atom sitting down here, and then you can manipulate it. You can turn on resonant tunneling and so on. And of course, there's a small probability of holes, which we don't care because that would be just empty plaquettes, but there could be also 2 atoms per plaquette, which we remove. So the idea is that this initial loading, where we can put 2 atoms then on one side, we increase the lattices to a very deep value and remove them by inducing inelastic losses. So then we remove the double occupancies and are left with single atoms in the plaquette.
Great, thank you. There's also a question from Michael in the chat.
Good question. I haven't thought about this. I would need to think about it. Yeah, I don't know. It's hard to tell, I think. So what happens, or what you are asking, is actually in the end, when we have the restored tunnel coupling between neighboring sites and long-range interactions, is somehow a model which is not a homogeneous lattice, but which has dimerized couplings, J and J prime, a flux, and long-range interactions. So I think that's a complicated phase diagram, which I'm not sure I know what all the various phases are that you would get in this case. Yeah. Also then depends on the filling. So it becomes actually complicated. We will go back to that. So depending on the flux that you realize per plaquette, and the filling, the number of particles that you put per plaquette, you can have various different quantum Hall phases. Like for the usual on-site interactions, you can even also have fractional quantum Hall phases. This I will say a little bit more about, but then with long-range interactions, I'm not sure what happens. Okay, so let me just make this comparison to synthetic dimensions, where now instead of having two real space lattice axes, we replace one by internal degrees of freedom. So this is a schematic. So this has been realized in a group of Ian Spielmann, but also at Lenz in Florence. And what you see here is this real space lattice axis along X, and the synthetic dimension, which could be different Zeeman levels. Here for ytterbium, M3½ -1½ and -5½ And then the coupling is induced by two photon processes. And these phases that appear also depend on the projection of the wave vector difference between these two lattice beams that induce the coupling and the lattice axis or lattice constant in real space. And if you want, you can also think about it as laser-assisted tunneling that I explained in the Floquet framework as a two-photon coupling. So we have also two laser beams that create this time-dependent potential, as shown here. And they are far off resonant from another internal state. So we have two photons that couple the same state, but via an off-resonant intermediate level. So you can also think about this as a two-photon process if you want. And recently, actually, this has been extended to more levels in the synthetic dimension using dysprosium atoms. And for dysprosium 162, there are actually 17 states that can be coupled in this synthetic dimension. And now you can look at various different things. So you can look at these skipping orbits that you have seen. So one is shown down here. So actually there's different blue shadings, different times during the evolution. So there's an initial state where then you see the skipping orbit. If you're prepared on the upper edge, you see the skipping orbit. But then if you're prepared in the bulk, I mean, if you have 17 sites, it actually makes sense to speak of bulk and edge quite well. Then you see that there are these nice cyclotron orbits that appear if you track the motion of a wave packet in this coupled synthetic plus real space dimension. Okay, and maybe just to finish, or just to give an outlook on what you can actually do with these techniques, is you can make it more complex in a sense that you can try to simulate quantum spin Hall physics. So if I mentioned that actually this technique relies on applying this linear potential in order to engineer the artificial field, which can be used by applying a magnetic field gradient. But now you can play with different internal states. So you can load different Zeeman sublevels into this lattice, which will see a different gradient. And in particular, you can choose two which have opposite magnetic moments. Okay, so you can choose two states that then see exactly the opposite potential for spin up and spin down. And we have done that with rubidium atoms, one prepared in F=1 and MF-1, and the other one in F=2 and MF+1. So they see opposite potentials, which actually introduces a change in sign of the artificial field that they see. And in the very simplest configuration, where those two spins are not coupled, you can generate the most simplistic quantum spin Hall system that you can think of, which would be two quantum Hall systems, where now one spin sees a band with opposite Chern number as compared to the other. And the first experiment that we did just to show that this indeed works is to use exactly the same lattice and laser-induced tunneling techniques and look at these lattice cyclotron orbits that I showed in the beginning, just to see that indeed the orbits have opposite chirality. So if you perform again this little toy experiment where you put a single atom in a plaquette, you see that for one spin state, the chirality is like this, while for the other spin state, it's the opposite. So there was a question about the dysprosium experiment. So in this case, it's a very good question. So in this experiment, if I remember correctly, the density is relatively low. So it's actually a 1D gas. It's like a tube shape, which is homogeneous along one direction and has this lattice synthetic dimension, such that the interactions are very weak and can be neglected. But it becomes very interesting if you include interactions, because now what you have along this synthetic dimension is infinite range interactions, because all the atoms interact with each other, no matter if they are on, say, side -8 or side 8, because it's exactly the same position in real space. And this can become very complex between the different internal states. And I think not even all the scattering lengths are known for the various different initial states that they have in dysprosium. And there can be inelastic decay and so on. So there's all sorts of complicated interaction processes that can happen in this coupled synthetic and real space lattice.
Yeah, I just wanted to mention, because I remember looking at this, I think because it's dipolar, the dipolar relaxation is really strong. So they have, and that's really an inelastic process. So they have some comments in the paper, maybe how to mitigate that. But I think that's something you have to confront.
Yeah, so actually the idea, but there are actually more challenges. So I think if I understand correctly, so the idea to get rid of this inelastic decay is to add like a magnetic field gradient in order to separate the tubes. So we'll actually induce a real space dimension by like separating the different J levels in space. But even then, I think the interaction between the different levels, it's not homogeneous. No, there are different scattering lengths. But I'm not an expert on dysprosium, so but indeed there's a comment in the paper.
Yeah, so I think now's a good time to transition to any final questions before we have our break before the next talk. So any questions for Monika right now are great. Otherwise, you can, of course, ask them in future lectures.
Or you can send me an email if you want. If it's very urgent and you cannot wait until tomorrow, you can also send me an email. Yeah, so that's anyway the last thing I wanted to say for today. Maybe I can show one last picture just to highlight other systems as well. So if you want to look up references, of course, these Floquet engineering techniques, they are not only implemented in cold atom systems, but also in superconducting qubits, coupled waveguide arrays, but also even in real solid state systems. So if you want to explore a bit more, there's a lot to read about these systems.
All right. So thanks for the great lecture, Monika, and we will see you tomorrow.
Okay, looking forward. See you tomorrow.
Thanks, Monica. See you.
Bye.